Look at this number. You know it is a 3. Instantly. Without effort. Now look at this one. Scrawled, lopsided, barely closed. Still a 3. You did not even hesitate. Your brain just did something staggering, and it felt like nothing. Here is the question I want to chase. What would it take to build a machine that can do the same thing? This feels easy, so we never notice how hard it is. You can recognize a 3 written 10,000 different ways. Thin, fat, slanted, shaky. No two are the same picture, yet you map them all to one idea. 3. Write down the rule you used. You can't. There isn't one you can name. And that is exactly the problem we have to solve. So let's start where the machine starts. To a computer, this image is not a number at all. It is a tiny grid. 28 pixels across, 28 down. 784 little squares. And each square is just one value. How bright it is. 0 for pure black. 1 for pure white. A gray is somewhere in between. That's the whole input. 784 brightness numbers. No threes. No shapes. Just numbers. Now meet the one idea this whole thing is built from. The neuron. Forget biology for a second. In a network, a neuron is almost embarrassingly simple. It is just a container that holds a single number between 0 and 1. We call that number its activation. 0 means the neuron is quiet. 1 means it is lit up, firing. That's it. A neuron is a thing that holds how strongly it is on. So take those 784 brightness values and pour each one into its own neuron. Now we have 784 neurons, one per pixel, each holding how bright that pixel is. Bright pixels, lit neurons. Dark pixels, quiet ones. This is the first layer of the network. The input. It is literally just the picture turned into a column of lights. Now jump to the other end. The answer. At the far side we put just 10 neurons. One for each possible digit. 0 through 9. When the network runs, each of these lights up a little. The one that lights up brightest is the network's guess. If the 10 neuron lights up to nearly 1, the machine is saying, I think this is a 3. Input on one side. 10 answers on the other. Now we need what goes between. Between the input and the answer, we stack a couple more layers. We call them hidden layers because we never look at them directly. And here is the hope. The beautiful, unproven hope. Maybe the first hidden layer learns to spot tiny edges. Little strokes of light. A short curve here, a straight bit there. Maybe the next layer assembles those edges into pieces. A loop at the top. A vertical line. The fork of a 3. And the last layer puts the pieces together into a whole digit. Edges, into parts, into numbers. Why build it in layers like that? Because that is how hard problems come apart. Recognizing a loop is easier than recognizing a whole 3. Recognizing an edge is easier than recognizing a loop. Each layer solves a slightly simpler question and hands its answer up. So if the machine could learn to detect edges, then parts from edges, then digits from parts, the impossible task becomes a stack of possible ones. That is the bet. Now, how does one layer actually talk to the next? Here is the machinery. Every neuron in one layer connects to every neuron in the next. And every one of those connections carries a number, a weight. A weight is just how much this neuron cares about that one. A big positive weight says, if you are lit up, I want to light up too. A negative weight says, if you are on, push me down. A weight near zero says, I don't care about you at all. The whole intelligence of the network lives in these weights. So what does a single neuron actually do? It looks at every neuron feeding into it. It multiplies each one's activation by the weight on that connection. And it adds them all up. Strong connections from lit neurons pull the total up. Negative ones drag it down. One neuron, one weighted sum. That number is the raw evidence for whether this neuron should fire. But sometimes a neuron should stay quiet unless the evidence is really strong. So we add one more number. A bias. Think of it as a threshold the sum has to clear before the neuron wakes up. A high bias makes a neuron hard to convince. Skeptical. A low one makes it eager to fire. So now every neuron has its own weights and its own bias. Its own little opinion about what it takes to light up. One last touch. That weighted sum could be anything. Wildly big, wildly negative. But a neuron's activation has to stay between 0 and 1. So we squeeze the number through a little squishing function. Huge positive numbers get pressed toward 1. Lit. Huge negative numbers get pressed toward 0. Quiet. And the in-between gets a smooth, gentle middle. Weighted sum plus bias squished into an activation. That is the complete life of a single neuron. Now zoom out and feel the size of this. Just one small network for our little digits has around 13,000 weights and biases. 13,000 knobs. Every single one a dial that can be turned, nudged, tuned. Turn them one way, the machine sees noise. Turn them just right, and a column of 784 lights flows through the layers and lands, cleanly, on 3. The whole question of intelligence becomes one question. What setting of the knobs makes it work? So step back and see what a neural network really is. Not a brain. Not magic. It is one function. A very large one. Pour in 784 numbers, and out come 10. And everything in between is just weighted sums and gentle squishes, repeated, layer after layer. We did not tell it what a 3 looks like. We built a machine with 13,000 knobs, and the only thing left to do is teach it to tune itself. That tuning has a name. Learning. And that is where we go next.